All right, so let's talk about the last section for calculus 1, okay? And the fundamental theorem of calculus, FTC. Super important section, and it gonna support you for calculus 2 and 3, okay? And okay, before we go through there, let's look at another theorem, which later on, if you become a math major or engineers, I believe this mean value theorem you're gonna use in the near future, okay, in some of the either physics related course or some other courses. Anyway, it states like this. If we have a function which is continuous on this closed interval from a to b, then there exists one point c on this interval such that f of c equals 1 over b minus a times the integral from a to b fx dx. Okay? So this is what we call the mean value theorem. Okay? As you can see, guys, this is the area under the curve, right? And then over b minus a, which you see that it's the length, right, of this interval. That's what we call the mean value. Okay, the mean value. And let's interpret this in a graph. Think about it this, guys. If I multiply b minus a on both sides, as you can tell, on the left side, it gonna becomes b minus a parentheses multiply f of c equals integral from a to b fx dx. Now we already know the meaning of the right hand side if we assume fx is positive on the interval from a to b, like this graph. And then this integral is going to denote the area under this curve, right? And then on the right hand side, you can see that b minus a, which is the length of this interval, right? And then times f of c. In fact, we are actually looking for a height of a rectangle, right? Such that the width times the height equals the area under the curve. And let's see how to find the height. You see, guys, this is from a to b fx here. And do you agree that when I find the height, it cannot be lower than the minimum value here? In other words, there is no way this area of this rectangular gonna be the area under this curve, right? Either you cannot select any height which is greater, right, than the maximum value for this function, right? Because in that way, that area of the rectangular will be greater than the area under the curve. Now, the only situation is that you can think about it is possibly the height is something like this, so that you can see that for this part, I over the estimate, but for this part, hopefully this part can equal the area of this piece, so that this area of the blue rectangular gonna be the same as area under the curve, okay? As you can see that when you pick the height, you're gonna always have an intersection with the function, right? So this is what we call the c here, and correspondingly f of c, okay? So this is one way to interpret the mean value theorem. Okay, now let's move to another part, the fundamental theorem of calculus, part 1. Okay, part 1. Let's start with this, guys. You see, I drew a graph fx like this, and before my interval is from a to b, right? And then I can denote my definite integral, which is integral a to b fx dx. stands for the area under the curve. Now, let's think a little bit differently, okay? And I think I probably need to also change this index here. Now, let's do this way. If I have a function, let's call it f of t, okay? And if I select a confirmed number a on my defined interval and let my any interval to be x. And you can think about it, guys, this x is a variable. As you can see that when you move around the x, do you agree that the area under the curve between from a to x, it changes, right? Because if your x is here, you see the area is this part. If you move your x is here, and then you see that the area under the curve is this BC. In other words, if I write the integral, let's see, be very careful about this part. The integral, definite integral from a to x, f of t dt, you see the notation changes. Do you see that this integral gonna be one area under the curve function? In other words, different x, you're gonna have different areas under the curve, right? So we have a notation called, this is called the capital F of x, okay? And the fundamental theorem of calculus part 1, it says like this. If I have a function f is continuous from a to b, closed interval, and also correspondingly capital F of x is also continuous on my closed interval, okay? And meanwhile, I know that capital Fx, this function, it is differentiable, okay? On the open interval from a to b. And then magic things happens, okay? The derivative of this capital Fx, which you take the derivative for this integral part, right? And that derivative equals f of x. Okay, so this is the fundamental theorem of calculus part 1. And you think about it, this, guys, this is pretty amazing. Why? Because we learn integral here, right? We learn derivative here. The part 1 is kind of like a mesh all those two parts together and then build a bridge. So the derivative of capital Fx equals f of x. Okay. So let's look at two examples here. And first one, if I have a y equals integral from a to x t cubed plus 1 dt, okay? If I'm looking for dy dx, in other words, I'm taking the derivative of this definite integral based on the fundamental theorem of calculus. We can see that, in fact, we immediately can write our answer. Dy dx is gonna be, basically, guys, it's do you see that it's you substitute, right? Substitute t with x, so it's x cubed plus 1. Okay, x cubed plus 1. So we done for the first one. Now let's look at the other one, like this. So if we have y equals integral from x to 3, 3t times sine of 2t dt here. And if I'm asking to figure out what is dy dx here, and you know, we can use the fundamental theorem of calculus part 1 to deal with that. But you know, to apply that, you have to make sure that the definite integral, it must start with a constant index to a variable, which is x. Okay. So, but in our problem here is from x to 3. So we need to do a little bit simplification. In other words, this equals negative from 3 to x, 3t times sine of 2t dt. And remember, this is the first property of the definite integral, right? And after that, we can take the derivative with respect to x, apply the fundamental theorem of calculus. So, dy dx gonna be negative. As you can see, basically it's a simplification. It's a substitution, right? Which is negative 3x times sine of 2x. Okay? And we're done for this. Okay?